rigidity to the structure against torsion. They also take a lot of uh, in-plane stresses due to deck loading, that is primarily compression. Similarly, if you look at double bottom serves as space for liquid cargo. The space between double bottom and the outer bottom serves as space for liquid cargo. Also, double bottom plating serves as a longitudinal primary member of the ship, providing longitudinal strength. Each structural component in a ship serves with regard to structural loading. It serves various uh, to withstand various load conditions. The primary longitudinal members, as you know, withstand longitudinal hull girder bending. But apart from that, shell plating also withstands hydrostatic pressure, that is coming due to uh, uh, perhaps I can explain it this way, that is coming due to hydrostatics in the transverse plane, hydrostatic loading in the transverse plane. If this is the ship structure and this is the load at line, then you can imagine that the hydrostatic pressure increases as the depth of water. So, therefore, the loading on this plate goes on increasing linearly till the bottom, and so it is here. And on the bottom plating, as you are aware, pressure is always perpendicular to the surface on which it acts. There will be the same amount of pressure acting here on the bottom. Can you see that? So, if you look at the loading here, it is actually compressing the ship. This is quite different from the longitudinal bending for which the shell plating was meant. So, it also withstands compressive loading. This occurs in all structural members, that they have to play a number of roles in withstanding load as well as satisfying other operational requirements of the ship. If we want to define the major components of the of a ship, structural components of a ship, we can take this as an example, and from here, can you see the diagram? Yes. So, what do we have here? This of course is the shell plating, the outer uh, shell consists of steel plates which are thin, that is the thickness is small compared to the other dimensions of the plate. This is the double bottom plating. This is a longitudinal bulkhead. In this particular case, this is a longitudinal bulkhead. Okay. This is the double bottom plating. This is the bottom plating, bottom shell plating. Is it readable? This portion, the so called bilge, is also a part of shell plating. Then you have the side shell plating. And this is bilge plating. And the plate at the bottom here, this region, is the so-called keel plate, and this has an additional function of taking the load of the ship during docking. You can see that the side shell plate stops abruptly at the upper deck level, and so is the deck plating, which stops abruptly at the side shell transversely. So, both for the side shell and the upper deck plating, there is an abrupt stoppage at the deck corner. So, it must be understood that there must be continuity of the structures for the stresses to be distributed in a continuous manner. Now, since this deck and this side shell stop abruptly, there is a discontinuity of this in the for the deck plating in the transverse direction and for the shell plating in the upward direction. So, these plates, the end plates here and here on the deck, the last plating, and on the side shell, the last topmost plating, are of extra thickness for this reason. This is called, can you tell? Shear strake. And on the deck, stringer plate. Right. Now, if you look at how the shell plating and the inner bottom plating, that is double bottom plating, and the longitudinal bulkhead have been stiffened, you will find there are two types of stiffening done here. Can you identify them? In this particular diagram, that is why I have brought this diagram, to show you that there are two types of stiffening done on this cross section. If you look at the bottom, you see this, yeah, if you look at the bottom, these small things here, if enlarged, they would look like, can you see this? Is it visible? No? Sorry? Okay. So, what you have at the bottom is a section like this, and this is on the double bottom plating, and the bottom plating also this is like this. The remaining I am avoiding. I am only talking about strengthening of the primary shell plating, primary plating members of the ship, and the remaining is brackets and all. We will forget it for the time being, we will see it later. So, if you see this, these are called longitudinals. Why these are called longitudinals? Along the length of the, yeah, because they run along the length of the ship. Now, this diagram that I have shown you, the double bottom plating is strengthened longitudinally, the bottom shell is strengthened longitudinally. You will also find that the longitudinal bulkhead here is strengthened longitudinally, and the side shell also on the upper portion is strengthened longitudinally. But if you look at the bottom part of the side shell, this is not strengthened longitudinally. Can you see that? So, what is this strengthening? Yes, it has been strengthened transversely. So, normally in land structures, if you have got a thin plate which you require to stiffen for various load conditions, you use what is called a grillage. I am sure, have you been told about this? A grillage, which is a combination of strengthening members in both directions, and the calculation of the scantlings of the strengthening members is done considering the overall loading on the plate, as if the strengthening is being done both by transverse stiffeners and longitudinal stiffeners. In ships, on the other hand, we do not normally use a grillage structure. What we have is a plate like a shell plate or a deck plate or a double bottom plate or a bulkhead is strengthened either longitudinally or transversely. There are of course the other components there to support the longitudinals or transverses, but primarily we strengthen it by primary members in one direction only. Do you get it? Unlike a grillage, the shell plate for example, you can see this shell plate here is a flat plate. We could have strengthened it by a crisscross of longitudinal members and transverse members, but we haven't done that. What we have done is our primary strengthening in this portion has been by the longitudinal members, and we are putting transverse brackets at intervals. So, the hull girder is strengthened by either of the two strengthening techniques, that is longitudinal framing or transverse framing. Or combination of both. Okay. Now, I have shown here both longitudinal framing in this portion and this portion, and transverse framing here. When do you use which framing and what is its requirement? At what stage do you use what framing? You have learnt about longitudinal strength of the hull girder. You know the importance of moment of inertia, section modulus of the hull section. While calculating section modulus, you use longitudinal members, right? So therefore, if I have a ship strengthened transversely, then the transverse members will not be taken for calculation of moment of inertia. Therefore, the entire section modulus that must be required to withstand the bending of the ship must be provided by members other than longitudinals. Is that clear? So, that is one advantage with longitudinal framing system, that the longitudinals contribute to section modulus. In a transversely framed ship, this does not happen. There is another consideration. Since most of the ship structures are designed on either longitudinal framing or transverse framing, most of the elements are designed based on beam theory. You know what is a beam theory, isn't it? A beam supported at two ends by some means and loaded in the middle or continuous loaded, and that is a basic beam theory. So, if I am going to strengthen a plate by providing a stiffener, then I have to consider this portion of the shell plating along the stiffener as a beam and decide the section based on the bending moment on that beam, which will consist of a part of the shell plating and the stiffener. Okay, this is what you have all done, isn't it? So, what is important is how long is the beam. If you look at the geometry of the beam, two things are important. One is the cross section and the other is the length between two supports, isn't it? So, if the length increases, if you want to keep the stress level same, then the cross section will increase. Am I correct? So, and the cross sectional increase is not really proportional, but more than power of 1 to the increase in length. From the formula that might have been given to you in beam theory, you will find L square coming up. isn't it? So therefore, if the span increases, then the beam becomes bigger and bigger. So this is an important criterion. If you look at classification society rules for calculating the scantlings for frames or beams, deck beams or longitudinals in double bottom, you will find the section shape is dependent on the span of the beam or longitudinal or whatever. Now this span is basically distance between the primary supports of this beam that it is connecting. Am I clear? So what is a primary support? When you are talking about the main shell plating, stiffening of the main shell plating, the primary members are the shell plating itself, the keel plate, the double bottom plating and the deck platings. Now suppose I have got a single deck ship, only a single deck is there, and I want to frame it transversely. You can see the span of the frame will become so much, and as you can well imagine, it's very high. The frame will become, the transverse frame will become very big in cross section, therefore very heavy. On the other hand, if I put, if there is, if I can break this span, then the scantling will come down. Typically in a twin deck ship, if I do two decks now, the span reduces to this and this, right? And if you look at the transverse framing of a ship, of a twin deck ship, you will find this frame is of a smaller magnitude than this frame. If you look at the cross section of these frames, this will be of smaller magnitude than this. That is primarily happening because of the span. So this is with regard to transverse framing. Now imagine that this deck was not there. So this frame, if I wanted to do it by transverse framing, then this would have become something like this. The frame would have been so thick. So it would have been really big. So then it is not advantageous to me. I would not, if the span is very large, I would rather frame it longitudinally, where the longitudinal will give me, also contribute to the longitudinal strength, rather than a transverse framing. Now this, when I talk about this transverse framing and longitudinal framing, if I frame a deck transversely like this, I have this main deck breaking the span, no doubt, but do I not strengthen this portion longitudinally at all? Or inversely, if I have a ship which I have framed longitudinally like this, do I not frame it transversely at intervals? What gives the transverse strength? That is strength against torsion, particularly the twisting stresses that are developed. What gives the strength if I do not have a transverse member? So that I have to also do. So after doing this, we have every regular interval, maybe third or fourth frame, we give transverse stiffening to these longitudinals. But the longitudinals are more primary than transverse in this case. In a transverse, in a longitudinally framed ship, these are designed first, and then the transverse stiffening is designed based on the longitudinal strength. And the inverse is the case in case of transverse framing. Do you understand? I give you another example, very interesting example many times designers face in a design office. The hull girder, this, sorry, deck girder. This is the hatch opening, right? And this, there is a bulkhead here, there is a bulkhead here. Now this hatch opening has to be strengthened by hatch side girder, that is on the side of the hatch the girder has to run, and transversely they have to strengthen by, what are these called? Hatch and beams. These are very deep structures. These are hatch side girders running on the sides, strengthening the opening you have made of the hatch, and hatch and beams. Now, which are the primary members? How do you design these girders and beams? If you take the bulkheads as your primary support, then the girder is designed first, and so that girder breaks the span for the hatch and beam. That means the hatch and beam becomes smaller. This part is designed with this span, this part is designed with this span, and this part is designed with this span. Okay, but the girder is very big because as you can see the span is large. You could reverse it. You could take this as the primary member. That means the span of this will be from here to here. Same here. You take the span from here to here, and the girder span will reduce and you will have smaller girders. Can you see that? Yeah, that's up to how you design it. How you design it. If you see one more thing, you may note that the hatch and beams are transverse members. They will not contribute to longitudinal strength. So, if you design the girders taking this span, then the girder is of bigger dimension contributing to longitudinal strength, where the girder is right at the top. Therefore, its contribution is much more, isn't it? Yes or no? You have done I by Y calculation, isn't it? You calculate I about the neutral axis. So, if it is farther away, its contribution is more. So, since we are talking of the deck level, if I design my girder as a primary member, then its contribution to moment of inertia is much more. Okay. So, based on this, you decide whether you will have a transversely framed structure or a longitudinally framed structure. And as I have discussed, every single element of the ship will have to be designed based on beam theory, simple beam theory, where you consider the primary members and the support system. This is essential to this. Even if you do uh, analysis in more sophisticated manner, the initial design is always done on this basis to get the structural layout done. After that, you can do refining of the design, calculation of the stresses, etc., by using sophisticated analysis techniques, numerical analysis techniques. There are certain other things we must remember while doing a structural layout. Structural alignment. What is the meaning of structural alignment? Once a structure is stressed, it should be possible for us to design the structure in such a manner that the stress lines are continuous, or there is no abrupt changes in stress levels in the structure due to uh, defects in layout. One such defect can be if there is structural misalignment. What does it mean? Every structural member must be aligned. See, just now one of you said that the girder is laid first. What does this mean? Girder is laid first. That means in a ship the girder is placed between bulkhead to bulkhead along one hatch side first, then only hatch and beams come. Now what happens to the girder in the next hold? What happens to the girder in the next hold? You have to have a break in the bulkhead. Bulkhead is a breaking the girder. So how do you continue the girder on the other side? Is it so that we should cut the bulkhead, run the girder, and then put closing plates on the girder? Should we do that? Or closing plates on the bulkhead? Should we do that? Or what should we do? How do we maintain continuity of the girder and also alignment? Alignment can be done or not done by two means. One is design, the other is actual erection. If I am passing a girder through the bulkhead, automatically my girder on the other side is aligned. But it's a very difficult process in shipbuilding terms. We normally don't do it. We'd prefer to bring the girder to the bulkhead, weld it there, and another bulkhead, weld it on the other side, provided the bulkhead can take welding on both sides.
It means that the integrity of the bulkhead is priority.
That is how it is done with an assumption that welding makes a continuous structure. Therefore, the girder, if it is aligned in line, its continuity is maintained. Now, as I said, one is layout in the design layout. In the design stage, you lay out the girder in a straight line. Another is in the erection stage. When I am bringing a girder on one side and another girder on the other side, I must make sure that they are in the same straight line. Even a little misorientation can cause severe cracks. So, alignment has to be done properly. So, you see, you have got a, let us say, a deck which is, let us say, which is closing in like this towards the forward end, right. You got a hatch opening here on this hold which is this big, and on this hold there is a hatch opening which is of lesser width. Now there is a bulkhead here. Your girder is running like this girder is running like this. You can see it is not aligned, right. What do you do? Do you leave it like this? How do we bring in alignment of the structure? How do you ensure that stress lines are continuous? There is no generation of excess stress at this because of abrupt stoppage of the girder. Or take another case, give a case where I am drawing the plan, shell plating, there is a deck here, there is a deck on this side, an intermediate deck. On this side, no deck on this side. This deck is finished. Okay, so this is abruptly changing here. What do you do here? Particularly, we should be concerned about this portion. So, how do we take care of it? These two cases I have shown you. How do we take care of this? How do we maintain the continuity of a major structural element that seems to be discontinuous? So, there are two ways we can do this. One is, if I have the girder going like this and I can crank my girder. If I can crank my girder, then the continuity is maintained. Yes?
Cut all these pieces, not in straight line.
No, 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 no. Girder is what? Normally they are pretty big. If I draw the cross section here, this is the hatch opening. The girder is like this. It's a L shape normally. And since it is very big, you don't get a rolled section. It is a fabricated section. So if I am having a L beam here, this plate is what is shown here, this point in the plan view. That means the girder is running like this. All I do at this stage is I just change the direction of the girder. Yeah, I mean you have a weld here. It's also a straight plate. It's also a straight plate. It's a cranking you are doing at this point and this point. This is one method by which continuity can be maintained. The other method is what we would use here in the second case I showed on the deck case, that at the corners we have brackets for continuity. That means I can have a big supporting bracket here in longitudinal direction. You understand, the girder is coming here like this. I have a bracket like this. My girder is going like this to bulkhead. Apart from that, I have a bracket with a flange at the bottom. And here I also have a bracket. Then the continuity is somewhat maintained, making some compromises. This is typically what is done in this case. You see, if the shell plating is stiffened like this and the bulkhead is stiffened like this, and this side of the shell plating is again stiffened like this, I can have a bracket, biggest dimension, you know, something like this. Okay, it could end on a this thing. For welding purposes, if you ends on a this thing is better, but this side the stiffeners on the other side, it doesn't really matter. You can, so this deck is more or less this corner you are spreading over a longer distance. But this is as regards the layout is concerned. What about the material itself? For example, let us say again take this case, take the same case. Here the bulkhead distances are pretty high, say about 25 meters. On this side the bulkhead distance is 15 meters. So the span has reduced. So this girder has a scantling of say this magnitude, and this girder has a scantling of say this magnitude, much smaller. Or take the case of a shell plating. Your keel plate thickness, which is thicker as I said because of the docking purposes, which is 20 mm, and the next plate is 10 mm. The plates are aligned. The 20 mm plate can be welded to a 10 mm plate. But is the continuity of material maintained? The answer is no. There is an abrupt change in the quantity of material. Same will happen here. It happens all over. Wherever you are designing structures, some plates you want to make it thick, and some plates where loads are less you want to make it thin. So can you weld a really thick quantity of material and to really small quantity of material and call it continuous and aligned? The answer is no. There must be a gradual change in the material quantity as well. That is, if you have got a 20 mm plate and you got a 10 mm plate, then you must have, if you have got a 20 mm plate and you got a 10 mm plate, then there must be a portion where this 20 mm plate will be cut like this, so that the change is gradual over the distance.
Will it always have to be on the side, cannot be in the center, and then both sides reduce?
Yeah, you can, yes, you can do that. You can do that, but it means more work. Depends on your requirement. Depends on your requirement. Even if you you see, the other thing I wanted to tell you is about stress concentration. Whenever we cut a plate, we produce a discontinuity in the material, and that discontinuity generally gives rise to concentration of high stresses at that location. So how do you take care of stress concentration? How do you take care of? Typical example is hatch corners. We have many cuts in the
Doubler plates.
yes. You could give double plates. That is adding extra material at that place so that just it can withstand more stress. Yes, but even the double plate, remember the same thing we discussed. That suppose I have got a deck plate running like this is the cut, and I want to put a doubler plate here, a real thick doubler plate. Then same there is a discontinuity coming up here, so you have to give something like this. What else can we do? We can put a stiffener at the end. The edge can be stiffened. What else can we do? If see the stress concentration is high, there is no doubt about it, but you have to locate, I mean a good design practice should be to decide whether this is coming in high stress zone. Suppose the stress level in that area is generally low and your opening is designed properly, though there is a little high stress concentration, it may not go up to the danger level, then perhaps there is no reason to worry. But if you are talking about the upper deck is normally a high stress zone because the stresses are bending stresses are maximum in upper deck, that to top layer. So then you have a problem. So while designing openings etc., one has to see whether the opening could have been avoided. That's the best. You don't have an opening, then there is no problem. Secondly, find out whether it is in high stress area. If it is high stress area, then of course you have to take proper care. Then corner, the various views one can analyze and find out. Normally, if the corner is rounded rather than a sharp corner, then the stress concentration is lower. Stress concentration will be generally higher near the opening, but if it has a sharp corner, then the stress concentration is higher than if it is a having a large radius of curvature. Then compensation. How can you compensate? The compensation is double plates or end stiffening. These are the normal this thing. If you don't do, then some diagrams given in books I can sketch out to you. You have so this is the side shell of a ship. This cut is given for ladder, gangway ladder, let's say, and this is the upper deck. Okay, this is that extra material you take up before the bulwark. You have seen a good ship cross section, I hope. That is the shear strike is extended a little bit above the molded lines, and then there is a gap, and then the bulwark plating comes up, right? So this is that extra plate. Now, if you have a cut like this, you normally think it's not important, but you have cracks developing like this because of this discontinuity. Plus, there is a welding here also. So, uh, okay, then how is the cross section of a bulk carrier? Let us say if you normally look at the cross section of a bulk carrier, this is the hatch side hatch combing, and this is the hatch side girder coming down here, and you have got a uh, top side tank, right?
Wing tank.
Yes, top side top sloping wing tank. What is the angle of this? This is what you had asked. The angle of this uh, side tank, how much should it be to the horizontal? We had said that it should be more than angle of repose. You asked about angle of repose, no, Mr. Mukherjee? Angle of repose you had asked, no?
Yes.
Angle of repose is the angle when you dump a bulk cargo in bulk, is the angle that the top makes with the horizontal. This is called angle of repose. The cargo, the general suppose flat surface, I pour cargo, bulk cargo, then it will make an angle to the horizontal. It will not become flat.
This is the curve of the cargo.
Yeah,
Yes.
yeah.
But after some time it will horizontal.
It will never make it. It will never make it.
Yes.
Yeah, it will settle, but it will still, it will settle. It will come like this.
What
Okay.
impact does it have on the ship's stability?
Oh, okay. Uh, Let us look at a normal ship, then we will come back to bulk carrier. That is, let us look at a general cargo carrier, then we will come back to a bulk carrier. I have got the hatch opening here. This is my midship, sorry, center line. Okay. Now I start loading grain in this. Suppose it was a single deck ship. I start loading grain in it. The grain will uh, take up a shape as per its angle of repose, isn't it? So, suppose the grain angle of repose is 23 degrees. Then you will take up an angle of 23 degrees, it will go like this, where this is the angle of repose. Okay. And you close the hatch cover comes here. Okay. And then the ship goes on its voyage. As you said, during the voyage the grain settles. Roughly 2% of the volume it settles. It's quite a lot. So this angle will come down to something like this. It will come to here. And same in this side. Now when the ship heels, there is empty space here, there is empty space here. So the entire grain will move from one side to the other. Suppose the ship is heeling to this side. Now along with it, this side grain will move to something like this, filling up this empty space because the space was available. What does it do? It will not go. So if space is available, it will go. So that means material is moving from one side to other. That is further adding to the rolling, to the heel angle that the ship experiences. This is also causing a heeling moment, weight moving from one side to the other. So it's coming, causing additional heeling. Now imagine the entire length of the ship, this is happening. This is very high. This behaves like a free surface. It behaves like a free surface. Loose grain behaves like free surface. If the ship comes back to the other side, the entire grain from that side will come to this side. It's like the water surface. It is free to move. It has free surface equation has been derived for you. You have got that small it divided by v, that was derived. So you know that because of the triangle moving from one side to the other, the loss of gm is there because of that. Same thing happens here. Now this is very large because it happens across the entire width of the ship. So what can we do? Immediately comes to mind that can I not break the width? Two things you can do. If I fit a tank here, then this will not shift. This portion is not contributing anyway, it's only within the hatch, this and this. Do you understand? If I block this space, then the empty space is not there. My grain is taking its automatic shape like this. Clear? So that is why bulk carriers have these top side tanks. But suppose you are carrying grain in a general cargo ship. What can you do? Suppose you are carrying grain in a 2-deck ship. Let's consider this. It's very interesting. You don't have this structure because it's not a pure bulk carrier. You require volume, you have space for general cargo. Now what will you do in this ship? This is still likely to shift. What can I do? One thing I can do, can I break this breadth of the ship? If I can break the breadth, suppose I could have some sort of a bulkhead here. Then this side will take a shape like this. That means the moment it will be from here to here only. Also the same thing this side. Do you understand? It's much reduced. So about 8 times or 10 times or 12 times reduced. How can I do this in a general cargo ship? This is the so called grain shifting boards. You have these boards stacked somewhere in the ship. When you want to carry grain, you fix this and then load grain. These are temporary bulkheads. Of course, you can go a step further. You require hatch covers for the twin deck. The hatch covers can be designed in a manner that they can fold up and form the grain shifting boards. Okay. One question I will ask you. If you have got these grain shifting boards, what happens to space here? This also, this grain will not fill up, no? This grain will go like this. So this is still moving here. How do you attack that? In a general cargo ship, in a 2-decker ship, in a few voyages you are going to carry the only carrying the grain. You are not continuously carrying grain, but some voyages you are carrying. For that you have made arrangements for the upper deck. What about this portion? Sorry? It can come down. That is down here like this. Like this. Then what goes here? So we can have some pull type of arrangement so that the grain can be put out from there. Right. An easier option will be if I can have access here. I cut large openings with gratings and temporary covers so that when I carrying general cargo, that can be closed. You know, not watertight. My watertight envelope is this. I don't require any watertightness here. So I could have some cut with grating. Okay, so these are some of the things you can consider, but remember that as soon as I cut, my deck becomes weak. On the other hand, twin deck is very near the neutral axis, stress levels are low. Is that correct? Stress levels are low in twin deck. Okay. Now tell me, these hatch combings are quite big in ships, isn't it? More than a meter high. Do we take them in longitudinal strength calculation or not? Hmm?
It will depend on the span of the hatch combing.
If I am not making it continuous, if my hatch combing is breaking between holes, there is no way I can take it. Remember our fundamental assumption that unless it material is continuous, I can't take it into longitudinal strength calculation. So though I am putting a lot of materials in the hatch combing, I can't take it to longitudinal girder strength calculation. It's not competent to contribute to longitudinal strength. Same thing with superstructure, huge structure, no strength, to longitudinal girder.
The hatch combing which are there, they are gradually tapered off to the bottom. Why is that?
Oh, that's for the hatch cover arrangement and to avoid discontinuity suddenly. So some tapering is there. So the material is not there at one point. So it is not continuous.
There is no material.
Yeah. So it's not continuous. Unless if you want to consider it to be continuous, you also have to continue the hatch combings beyond the hatches throughout the length of the ship. Yes. Sometimes it is done. Sometimes, but then you have the problem of movement transversely and so on and so forth. Okay. Thank you.